For 48 hours, spread out across an entire year, a telescope 1 million miles from Earth pointed straight at the most dangerous object in our galaxy, and it did not look away. That object is Sagittarius A star, the supermassive black hole sitting at the exact center of the Milky Way. And when the James Webb Space Telescope finally gathered enough time staring directly at it, what came back was not calm. It was not steady. It looked, in the words of the scientist who led the study, like it never stops bubbling. That single detail is what unsettled the astronomers who spent a full year collecting this data, not because something dangerous is heading toward Earth. It is not. But because the object sitting at the very heart of our own galaxy is far more restless, far more chaotic, and far less understood than anyone expected, even after decades of study. So here is the real question worth asking. What did James Webb actually see when it finally got a long, uninterrupted look at our galaxy's black hole, and why does its behavior still make scientists uneasy? Let's start with the basics, because Sagittarius A star is not like the black holes. Strong, unusual radio signal coming from that exact location. It would take decades of careful observation, using multiple telescopes and multiple types of light, before scientists were confident enough to call it a black hole and give it the name it carries today. Here's the part that matters for this story. A black hole itself gives off no light. By definition, nothing escapes it, not even light. Itself, once matter crosses a boundary called the event horizon. So astronomers can never actually see the black hole directly. What they can see is everything swirling just outside it. A spinning ring of superheated gas and dust called an accretion disk, slowly falling inward, glowing brightly as it heats up under enormous gravitational stress before finally disappearing forever. That glowing disk is what James Webb was. Because Webb observes primarily in infrared light, a type of light that passes through cosmic dust far more easily than visible light does, it can see straight through the haze that has blocked earlier observatories for decades. Even with that advantage, actually studying Sagittarius A star in real time required something ambitious. In 2023 and 2024, a research team led by astrophysicist Farhad see exactly how this object behaves over time, rather than catching only a brief, single glimpse. What they found surprised even the scientists who ran the study. They expected to see flares. Black holes across the universe are known to occasionally flare up, brief bursts of extra brightness caused by disturbances in the material swirling around them. What the team did not expect was just how constant that activity would turn out to be. According to the study, published in the astrophysical journal Letters, Sagittarius A star produced somewhere between 5 and 6 major flares every single day, along with a continuous stream of smaller flickers happening in between them, some lasting only a few seconds at a time. Yousefzadeh described it plainly in the team's official statement. "It is always bubbling with activity," he said, "and it never seems to reach a steady state. Every single observation session showed something different from the one before it. This is the first real turning point in the story, because it forces a specific question. If this black hole never actually settles down, what is causing all that constant chaotic movement in the first place? The leading explanation involves magnetic fields. The gas swirling in the accretion disk is not simply falling inward in a smooth, orderly stream. It is turbulent, compressed, and threaded through with powerful magnetic field lines. Scientists believe that when two of these magnetic field lines cross and suddenly reconnect, they release a burst of energy, flinging nearby particles to extremely high speeds, almost the speed of light. Those energized particles then give off the bursts of radiation Webb detected as flares. It is a process similar, on a vastly more extreme scale, to how flares erupt from the surface of our own sun. That explanation accounts for individual flares. It does not fully explain everything Webb saw, and this is where the story gets more specific and more genuinely puzzling. The team noticed something they had never been able to measure before. When they compared the timing of brightness changes at slightly different wavelengths of infrared light, They found a small but very real delay between them. The longer wavelength signal consistently lagged behind the shorter one, sometimes by only a few seconds, sometimes by as much as 40 seconds. This was the first time researchers had ever captured that specific kind of time delay in this part of the light spectrum. Why does a few seconds of delay actually matter? Because it hints at two separate, how particles behave in the extreme environment right next to a black hole's edge. It is important to be clear about what is confirmed here and what remains an open, active question. The existence of the flares, their frequency, and the measured time delay between wavelengths, these are confirmed, directly measured results from real observational data. The exact explanation for why the delay happens, and whether it points to one specific physical process or a combination of several, remains a genuine scientific question the research team is still working through. Yusuf Zadeh himself said as much, explaining that his team suspects two separate processes are responsible for the short bursts compared to the longer flares, but that the full picture is not yet settled. Barely a year after this study came out, a completely separate discovery added another R layer to the story, and this one came from an unexpected direction entirely. In 2025, a different research team pointed Webb's mid-infrared instrument at Sagittarius A star and detected something that had never been recorded before, a flare specifically in the mid-infrared range of light. This might sound like a small technical detail, but it solved a genuine long-standing puzzle. For over 20 years, astronomers had separately observed flares from this black hole in radio waves and in near-infrared light, but nobody had ever been able to connect the two. There was a gap in the middle of the picture, a part of the light spectrum nobody had been able to observe clearly. Webb's new mid-infrared detection finally filled that gap. The team also caught something else happening at the same time, using a separate radio telescope called the sub-millimeter array. They detected a matching signal roughly 10 minutes after the mid-infrared flare appeared. That delay itself carries meaning. It suggests the flare does not simply appear and disappear in one place. It travels, evolving as it moves, cooling down and shifting into longer wavelengths of light as time passes, exactly the kind of behavior scientists would expect if the flare truly is, caused by a burst of energized particles gradually losing their energy after being accelerated near the black hole's edge. So by this point, two independent studies, using different instruments and different research teams, had each found real evidence supporting the same general picture. This black hole is not simply glowing in a steady, predictable way. It is constantly erupting. Light years away, safely outside any realistic zone of influence from activity at the galaxy's center. Nothing about these new observations changes that basic, reassuring fact. What has genuinely changed is our understanding, not our safety. For decades, scientists had only fragments of this story. Isolated flares caught in single wavelengths, gaps in the data nobody could fill. and no real sense of just how constant and chaotic the There is still real uncertainty left in this story, and honest scientists are the first to say so. Researchers do not yet fully know whether the flares repeat in any kind of predictable pattern, or whether they are essentially random every single time. Yousefzadeh himself said the team hopes to eventually observe the black hole for a full, uninterrupted 24-hour period, specifically to help answer that exact question. Until that observation happens, the honest answer is that nobody knows for certain. So return to the central question this video started with. What did James Webb actually see when it finally got a long, clear look at Sagittarius A star, and why does it unsettle scientists? The answer is not a hidden danger, and it is not evidence of anything threatening to Earth. What Webb revealed is a black hole that behaves less like a calm, sleeping giant and more like a restless, constantly shifting storm, erupting in flares almost every single day, glowing across parts of the light spectrum nobody had ever clearly measured before, sitting at the exact center of the galaxy we call home, close enough to a nearby star that scientists can now watch water quietly forming in its shadow. That restlessness is exactly why it unsettles the people who study it closely. Not because it threatens us, because after decades of assuming the heart of our galaxy would eventually reveal a calm, orderly system. Once we looked closely enough, Webb showed scientists the opposite. The closer they look, the more chaotic and alive it turns out to be. And somewhere in that constant, flickering 26,000 light-year distant storm sits the true physical engine at the center of everything the Milky Way is quietly built around.